All right, so this is gram to gram stoichiometry, and this is the next step you would take after learning how to do mole to mole stoichiometry. And some things are a little bit different, and a lot of it is very similar. So let's take a look at some of this stuff together. So just like with mole to mole stoichiometry, you need to have a balanced equation to do these problems right. And again, it's really important to make a balanced equation. You have to be really good at putting your formulas together. That's really, really important here. So let's take a look at an equation that we have seen before. This is the synthesis of iron 3 oxide from iron and oxygen gas. And we worked with this equation when we did mole to mole, so we can just carry over some of those skills. So here's the kind of question that you would be asked in a gram to gram stoichiometry problem. If 234.67 grams of iron react with excess oxygen gas, how many grams of iron 3 oxide are produced? And so if you compare that to the kind of question you're asked in a mole to mole question, you can see that it's not that dissimilar. So this would be like an example of mole to mole. So we had a number of moles given to us in the problem, and then we wanted to know how many moles of iron 3 oxide were produced. And in this case, with the gram to gram type problem, you're just, instead of starting with moles, you're starting with a number of grams, and then we're asking for the production in grams, not moles. So that's pretty similar. It's just the skill that you need to have here is the ability to convert between moles and grams, and that's something we can do now, so that's easy. Okay, so the schematic for this, or the dimensional analysis setup that you would use, is pretty similar but a little bit different than the mole to mole. You can see it's got a few more spaces to it here. So we still work with chemical A and chemical B, and remember that chemical A is the chemical that is given to you in the problem with a quantity. So we know how much of A we're starting with, and then B is the chemical that we're asking about in the problem. In this case, the iron, we have the amount of iron that we're starting with, that makes it chemical A, and then we're asking about iron 3 oxide, and so that makes this chemical B, okay? And I won't talk too much about A and B anymore because you should know what those things are at this point. So when we put these values in, the best thing you can do, I'm gonna really recommend that you do this right off the bat, and that is to put the molar masses of the chemical A and B underneath the symbols or the formula for those chemicals. You're gonna need to use them. Calculating molar mass is just one of those tedious things that you got to do all the time. So just get it out of the way quick. Iron's an easy one, 55.85. That comes off the periodic table, and just write them right underneath the symbol here like this. And then 2 irons and 3 oxygens gives us 159.70. Okay, so you just have those numbers handy. We're not going to do oxygen because it's the excess reactant. We don't need to worry about it in this problem. Okay, so according to this dimensional analysis table, here's how those numbers would go. Okay, we're gonna see our grams of A. We've defined iron as A with its molar mass down here. So maybe I'll try to keep this in view like that. Okay, and then we've got the coefficients that come from the balanced equation. So the coefficient from our chemical A, iron is a 4, so that's gonna go here. And then the chemical B, the iron 3 oxide, it's got a coefficient of 2, so it goes there. That's the mole ratio part of the problem. And then the molar mass of chemical B, that goes right here, and that's the 159.70. Okay, so now it's just a matter of multiplying across the top of the fraction and then dividing by the product of the bottom. So I think it's good. I do it this way where I actually treat this just as a fraction, and I'll just multiply the numbers across the top here and hit the equal sign. So I'll go ahead and do that here. So, oops. So we go 234.67, times I'm gonna leave the ones out because they don't do anything, times 2 times 159.70. Here I'll just hit the equal sign. Keep that number on your calculator. You don't have to round it or anything at this point. And then divide by the product of the denominator here. So divided by, and then in parentheses, when you have a couple of numbers that you got to multiply, just put the product in parentheses. So parentheses 55.85 times 4, close those parentheses, hit the equal sign, and then we've got to round this to our significant figures that we're limited to, which is 5 here from chemical A, the starting quantity of chemical A, and that gives us 335.51 grams of Fe2O3, okay? And that's how that goes. It's, so it's a little bit more complicated than mole to mole, but not a ton more. And you can see that we're only comparing two chemicals at one time here. And so let's do another problem just to get this solidified. So here's working with the same reaction, which I guess I'll try to show you here. There we go. So same reaction, different problem. How many grams of oxygen gas are required to fully react with 218.62 grams of iron? So here we're comparing our chemical A and B are both our reactants, and that's fine. Remember, A can be a reactant, B can be a reactant, or we could work with a reactant and a product, or it just doesn't matter. The A and the B scheme, the A is the whatever you know the amount of, and the B is what you're asked about in the problem. So in this case, iron is A again, and then how many grams of oxygen gas? That means that this is our chemical B, all right? And so those numbers then would go into that table like this. We have our starting amount of chemical A, 218.62. Here's the molar mass of chemical A. The mole ratio is right here, the 4. That's the 4 from the iron, and then the 3, that's the 3 from the oxygen, and then the 16.00 grams. Oh, you know what? This is not 16.00 grams. Sorry. This is O2, so that makes that 32.00 grams. My bad. O2, so you got to put the chemical formula, the mass of the formula here. And so we can go ahead and calculate this just like we did the last one. I'm going to multiply the numbers across the top and hit the equal sign. 218.62 times 3 times 32. Hit the equal sign and then divide by the product of the denominator here, which is 55.85 times 4. Something has gone wrong here. Let me redo that one. 218.62 times 3 times 32 equals that divided by, I must have cleared it the first time, sorry. 55.85 times 4. Leave out those ones again. And our answer here is 93.946, okay? 93.946 grams of O2, okay? And that's our answer here, all right? So these problems aren't so bad, I don't think, but it does take some practice. Now, what you're calculating here with these stoichiometric calculations here, these are known as theoretical values. Theoretical just means that, like, on paper it should do a certain thing, like mathematically it all should work out a certain way, and we just say that those are theoretical values. They're calculated values, okay? And oftentimes, though, in a lab, like if the reaction is actually being done in a lab, it's usual and very, very common that the actual value that you would produce is different than the theoretical value that you would produce. And so we need to do a couple of things where we have some percent error and some percent yield calculations. And so, like, I'll just kind of go back in time to this this problem right here, the first one we did. So this problem was about the production of a product, and we theoretically figured out that, according to this many grams of iron, we should, in theory, create or produce this much iron 3 oxide. The fact is that if you did this stuff in a lab, you'd probably produce a different value of this, and that's just because lab conditions can keep reactions from happening efficiently or whatever. It just never quite works out in an actual setting the way that it does on paper. And that's where these calculations of percent yield and percent error come into play. So percent yield is a very simple equation. It's your actual production or just an actual value divided by the theoretical value, and then times it by 100. Okay, so this will give you how much of how close to the theoretical value were you, and then your percent error. We've worked with this before. We're going to take the absolute value of the difference between the theoretical and the actual values, and then we're going to divide that difference by the theoretical value, and then multiply it by 100, and that gives you a percent error, and we've seen that before. Okay, so let's do a problem that involves these calculations here. So here is the problem in lab. So we're pretending that this is actually happening in a lab setting. So in lab, 424.68 grams of silver nitrate react with excess sodium chloride, and 310.25 grams of silver chloride are produced. That number is going to come back as an actual production or an actual value, and that's oftentimes given in a problem like this. So based on that, what is the percent yield and what is the percent error? And here, you got quite a bit of work to do because you don't have a reaction to work with. You are going to have to come up with that, and that's fine. I'll help you that. But what we want to answer to get these things, we have to have a theoretical yield. We've been given an actual value, but to do those percent yield and percent error, we have to have also a theoretical value. And so to find that, you've got to ask yourself this question: how much silver chloride should have been produced according to starting with this many grams of silver nitrate? So we're going to do a stoichiometry problem that's going to answer that question. All right, and so to begin with, you got to have your balanced chemical equation, and here it is. This one's nice because it's balanced without any coefficient numbers, so that just means there's a ones. Everything is in a 1-to-1 ratio. All right, so here's what you would do. You would basically treat that number of grams that you start with, of silver nitrate. That is your chemical A, and based on having a certain amount of chemical A, how much of chemical B should you be producing? So when you do the math here and you put it into our little dimensional analysis table here, these are where the numbers come out. And so these numbers are coming from silver nitrate. This is 169.91, and then the silver chloride is 143.35. Just calculate those numbers before you start, because you'll have to use them. So you do the math, multiply across the top, divide by the bottom, and you find that according to the math, 358.29 grams should have been produced, but only 310.25 were actually produced. So now we've got our theoretically calculated answer here that we can compare to our actual value in our percent error and our percent yield problems. Okay, so here's how those set up. Remember, this was our actual. That just comes from the problem, and then this is our theoretical. All All right, so we're just gonna divide those values and divide it by 100. So do that here, 310.25 divided by times it by 100, and that gives us an 86.592% yield. So that means that in the lab we produced 86.5% of what we should have produced theoretically. Okay, and then the percent error, oftentimes the percent yield and the percent error add up to 100, but let's just do the math according to the formula here. So we're going to take the difference between the theoretical and the actual. That's 358.29 minus 10.25. And if you end up with a negative number here, just make it a positive, right? So that number then divided by the theoretical 358.29 gives us times 100, gives us a 13.41% error, okay? And yeah, so that's how that goes. So really, I think the thing that you gotta really, this part is where the mistakes can be made. The question you need to ask yourself when you're in a setting like this is like, how much of the product should I actually, or should I theoretically make? And then you can compare that to your actual production, okay? So I hope that helps. We'll do lots and lots of practice with this stuff, and you gotta get good at this, because it even gets more challenging than this actually. So all right, that's it.